So when we try to solve a problem of a plane frame, like the one shown here, you can see that you can develop the stiffness matrix for individual members. We had discussed that already, that the stiffness matrix in local coordinate system for this member would be known. Likewise, the stiffness matrix in this coordinate system, 1, 2, 3, 4, 5, 6. So basically the active degrees of freedom are only 1, 2, and 6, and 7, 8, and 12 for this member too. So we can develop the stiffness matrix in individual coordinate systems for individual members, right? That's not a challenge that we had already seen in the previous day's class. Then the issue is that when we go about assembling the structural stiffness matrix, we cannot directly add the stiffness terms, which are, let's say, corresponding to 8, 8 here and 2, 2 here, even though this joint is same as this joint, but the direction of 8 is not same as the direction of 2, and therefore we cannot join those terms. So basically there is a mismatch here, and for that we have to change the stiffness matrix of either this term, this member, or this member, so that they are aligned together, they are aligned in the same direction. So obviously you can see that we call this direction as horizontal direction and this as the vertical direction. So member 1 seems to be aligned with the horizontal direction. So we will try to transform member 2, and we will assume that global x is in this direction, and member 1 has local x also in the same direction, but member 2's local x is not aligned with the global x, and that's why we will have to transform the stiffness matrix and other vectors for member 2. So that's what we started discussing in the previous class. Stiffness matrices were developed in the local coordinate system, but they cannot be added directly. So for that, we started with discussing how to transform a vector. Okay, so the vector had 3 components in this case. Let's say a vector A we were starting with. So if you have a vector A, it has 3 components, right? Now vector A need not have 3 components, and we will see several cases where it has more than 3 components. But for the time being, it has 3 components, vector A. Okay, so it has it has AX, AY, and AZ. That is in the out of the plane direction. Okay, so if I have to mark it as the direction of AZ is in out of plane direction. Okay, if I were drawing it like a cross, then that means into the plane. I'm drawing it not like a cross, but like a dot. That is out of the plane. Okay, so that is AZ. Now, that is in the structural coordinate system, these are the values: AX, AY, or AXS, AYS, and AZS. Now, there is another coordinate system, which is member coordinate system. Okay, like we saw in the case of second member, which is not aligned with the structural coordinate system. The relationship between the structural coordinate system and the member coordinate system is that you reach the member coordinate system from the structural coordinate system if you rotate the structural coordinate system in the counterclockwise direction by an angle gamma about axis Z. Okay, so axis Z does not change its location. Axis Z remains in the same location. We rotate the coordinate system about Z axis by an angle gamma in the counterclockwise direction, and we reach xm from axis. Okay, and that's how ym is also found, by moving ys by an angle gamma. Okay, so basically about the Z axis we have rotated the whole thing. Now in the new coordinate system, this same vector A can be written as AXM, AYM. Okay, so the same vector can be written as either AXS, AYS, AZS, or AXM, AYM, AZM. Okay, now obviously AZ value in S coordinate system and M coordinate system are the same. Okay, however, we did some calculation, some geometric calculation, some basic geometric calculation, and we found in the last class that if I know the values in the S coordinate system, that is AXS, AYS, AZS values, the values in the M coordinate system, that is AXM, AYM, AZM, can be calculated by using this set of equations. Okay, and these we had developed by using simple geometric manipulation. Fine. So this matrix, this is called transformation matrix for a 3x1 vector. Okay, so the vector has components in x, y, z direction, 3 components. If that is the case, we can transform it from structural coordinate system to member coordinate system by pre-multiplying by this transformation matrix. Okay, fine. Anybody had any doubt about this one? This is where we had stopped almost last time. Any doubts? Any questions? Now here, one thing you must remember is that this gamma is calculated counterclockwise from the structural coordinate system to the member coordinate system. Okay, so if you are measuring from the member coordinate system to the structural coordinate system, it will become clockwise. Okay, positive gamma. Similarly, if it is in the clockwise direction from structural to member, again that is negative gamma. Fine. So this convention of how gamma is taken should be remembered. Fine. So this is the transformation matrix. This transformation matrix works for any vector which has three components: one in x, one in y, one in z. All right. Moving forward. Now, in our So now you can also, so right now this equation is basically relating the structural coordinate system to member coordinate system. So if I know the AS value, I can get the AM values. So AM vector I can get by pre-multiplying with R. However, you can rewrite these equations or rearrange these equations to get AXS, YS, and ZS terms on the right hand side, sorry, on the left hand side, and AXM, AYM, AZM terms on the right hand side. Okay, and in the process, you will see that all that you do is you take the transpose of this matrix, which essentially means that, see, if you look at this equation and compare with this equation, basically this matrix here should be inverse of this matrix. Agree? Because AM was equal to R AS, then AS should have been equal to R inverse AM. Okay, but if you reshuffle these equations, these terms, you will see that you get this matrix, which is nothing but the transpose of this one. So basically what that means is that R transpose is also equal to R inverse. Okay, so you can write AM is equal to R AS, or AS is equal to R transpose AM. Okay, this is the particular type of a matrix which can have its transpose that is equal to its inverse. Okay, that is not true always, of course. But in this particular type of a matrix, these are called orthogonal matrices. There, this kind of a possibility exists. Okay. So now after I know this much, I can convert any vector value from the structural coordinate system to the member coordinate system. And if I know the values in member coordinate system, I can convert the values into structural coordinate system, right? By using this equation. Fine. Now, so far we can deal any vector that has three components: X component, Y component, Z component. Now, what you will see is that soon we are going to have to deal with problems which have more than three components. In a plane frame, at a node, you have three vectors, right? You remember that? In a plane frame member at a joint, you have 1, 2, and 6 degrees of freedom. So 1 is in X direction, 2 is in Y direction, and 6 is actually a rotation, but that is in the Z direction. That's how it is represented. Okay, so it has three components: X, Y, and Z, 1, 2, and 6. And that's why you can use this transformation for one joint. But oftentimes, we represent vectors in a bigger form. We represent them in 1, 2, 6, 7, 8, 12 form, right? Forces, we represent force in 1, 2, 6, 7, 8, 12. Then what do we do? What transformation do we use? So let me, we will go into this equation later. Just look at the left-hand side of it. Oftentimes, we will write the force vector or a displacement vector. So this is the displacement vector. This is the force vector. We will focus on the force vector only. A is action, right? Force. So the force vector is often written as AMJ followed by AMK. So there are 6 components now. 3 components of AMJ, that is force in one direction, 2 direction, and 6 direction at J joint. And AMK is 3 forces, 7, 8, and 12 directions at K joint. Okay, so you got total 6 components. So this is a vector of 6 components that I'm writing in this form. Okay. Now individually, out of these 6, individually AMJ can be written as R times ASJ, right? If you go to the previous slide, AM, that is any 3 component vector, can be written as R times AS. Same thing I can do here. So R times ASJ will be equal to AMJ. So likewise, R times ASK will be equal to AMK. Now, I can separate ASJ and ASK term into a single vector, and what I'll get is basically this matrix R00R. Okay, so now basically this new vector, that is my AS for combined J and K for the member, right? So this member has 2 joints, J and K. For them combined, this is AS vector. which has how many components? How many components are there in AS vector? People?
3.
AS vector has how many components? This entire vector? ASJ, ASK combined?
6 components.
Six components.
6 components, right? So those 6 components will be correct. These are 6. There are 6 components. So 1, 2, and 6 here, the way they are marked, they are in local coordinate system, member coordinate system. Okay, that is AMJ and AMK. Those are the forces. AMJ for these 3 and AMK for joint K. ASJ will be actually in, if I may draw, I'm worried that I'll make it very clumsy. ASJ will be in these 3 coordinates. Sorry, 6 will be CNS. I'm sorry. Will be in this coordinate system. You follow? So 1 will not be aligned with. So this one, this is global 1, that is structural 1. This 2 is structural 2. Okay. So they are not aligned with the local 1 and 2. But anyway, so you get 1, 2, and 6 of this one. Similarly, you will get 1, 2, and 6 here. Or you can write 7, 8, and 12 in the global coordinate system. Fine. So that 1, 2, 6, 7, 8, 12 of global coordinate system, that is this vector. Okay. And the transformation matrix required for that will be R0, 0, R. You can see that, right? Basically, if you do this multiplication, it will be R times ASJ plus 0 times ASK. That is basically R times ASJ. And the second row would be, second row, which is basically combination of 3 rows, will be equal to 0 times ASJ plus R times ASK. That is R times ASK. So that is equal to this one. Fine. Okay. Any doubts about this part? So now what has happened is, we knew the transformation matrix R, which was equal to cos gamma sin gamma 0 minus sin gamma cos gamma 0, 0, 0, 1. Okay, this was my R matrix. This took care of a vector that had x, y, z components. Okay, a three component vector that had x, y, z components. Okay, and it rotated or took care of the transformation due to rotation of the coordinate system. I'm not writing the entire thing. Rotation of the coordinate system about z-axis by an angle gamma in the counterclockwise direction. Fine. This is what this did. R vector, R matrix. Fine. But now there is another matrix I'm talking about, that is R0, 0, R, which can actually take care of a vector, or which can transform a vector. Again, the same thing. This description remains the same, but now it can transform a vector which has XYZ definition. Okay. If I had another vector, let's say XYZ, 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 XYZ. This would be basically a space frame, right? You remember, a space frame has 12 degrees of freedom. This is a space frame. You have 3 translations. You have 3 rotations, right? At each joint. So 3 translations first, that is first XYZ, the 3 rotations at joint J, XYZ, 3 translations at joint K, XYZ, 3 rotations at joint K, XYZ. So you got 12 vector. What would be the corresponding transformation matrix for this kind of a vector? What shall it be?
3 by 3 of diagonal elements with R.
Yeah, so can you tell me the first row?
R 0 0.
That's it. See, R will transform this one 0 0 0, right?
Oh, once more 0. Yeah.
Okay. So this kind of a transformation matrix will take care of 12 by 1 vector. That is like a vector like this. Clear? So for 3 by 1, you will just simply use an R. For 6 by 1, you will use R00R. For 12 by 1, you will use R0000, R0000, R0000R. Like this one. Got it? Straightforward, right? There is no mystery here. It's pretty simple. Okay, so, and this can be used for force vectors or displacement vectors. It can be a force vector or a displacement vector. That doesn't matter, right? So these values could be force values or displacement values. As long as the order is XYZ, 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 this will work. Fine. Now, what happens is that I have learned how to do this part of transformation here. And same thing is given here. That is for the displacement transformation. Okay. Okay. No doubts here, right? Now, that automatically has given us a lot of insight into how to do the matrix transformation. Okay. I knew the stiffness matrix of this member in this coordinate system 1, 2, 6, but I did not know its stiffness matrix in this coordinate system. Right? But what is stiffness matrix? Stiffness matrix is nothing but the relationship between the displacement matrix and the force matrix, or displacement vector and the force vector. That is what stiffness matrix is, isn't it? So in the local coordinate system, the stiffness matrix is relating the displacements in the local coordinate system to the forces in the local coordinate system. In the global coordinate system, or the stiffness in the global coordinate system, basically S, M, S, let me call it, would be actually relating the displacement in the global coordinate system with the forces in the global coordinate system, or S. So when I say S, it means structural or global. I will use the terms structural and global interchangeably. Likewise, I will use the term member and local interchangeably. Okay. Basically, I mean the same thing. When I say member coordinate system or local coordinate system, I mean the same thing. When I mean structural coordinate system or global coordinate system, I mean the same thing. And the notation here is S versus M. Fine. So here, this M represents in the member coordinate system. But if I write SMS, then it means stiffness of the member in the structural coordinate system. Okay. Fine. So that is SMS in the structural coordinate system. So basically, I had this equation to start with: forces in the member coordinate system, stiffness of the member in the local coordinate system or member coordinate system, displacements. I changed these two into vectors of force and displacement in the structural coordinate system, right? By doing these transformations, I can take this equation, I can call it RT. This particular matrix R00R, I'm calling it RT. For a plane frame, this is the size of RT. For a space frame, the size of the RT will be 4 by 4, R000, just like what we discussed just now. Anyway, we'll not go there yet. This is my RT. So the same equation I can write as RT AS SM RT DS, right? This is basically SM. Now, if I take this RT to the other side, it will become RT transpose SM RT DS, right? I'll take this RT to this side. So AS will become equal to something multiplied by DS, right? AS is equal to something multiplied by DS. Then what is that something? Whatever that thing is, that is basically my, what is it? The matrix that is relating AS with DS. What is that matrix? What do we call this matrix that relates AS with DS?
Stiffness matrix.
Yeah. So there was a matrix that was relating DM with AM. What are we calling that?
Member stiffness matrix.
Member
Stiffness matrix in member
in
coordinates.
the member coordinate system. So this one was stiffness matrix in the member coordinate system. Stiffness matrix in member coordinate system. And the matrix that relates DS with AS will be called stiffness matrix in structural coordinate system. Agreed? Right? Because this D and A belong to the structural coordinate system. Therefore, this is the stiffness matrix in the structural coordinate system. This D and this A belong to the member coordinate system. That was these local degrees of freedom 1, 2, 6, 7, 8, 12. That's why this was a stiffness matrix in the member coordinate system. Okay. Looks like you guys are not convinced. Somehow I'm not getting very enthusiastic response from you. Maybe it's just too simple for you, or anyway. So please let me know if you have any doubts anywhere you want me to repeat some parts. AS will be equal to SMS DS. Okay, this SMS is nothing but my structural, my stiffness of the member in the structural coordinate system. Stiffness of the member. This M corresponds to member in the structural coordinate system. Okay, which can be written as RT transpose or RT inverse SM RT. And as we had discussed, R inverse was equal to R transpose, and similarly RT inverse will be equal to RT transpose. So I can write that RT inverse as RT transpose SM RT. Okay. So if I know the stiffness matrix in the local coordinate system, I can do pre-multiplication with RT transpose and post-multiplication with RT. I'll get the stiffness matrix in the structural coordinate system. Got it? We will see through an example how to do this calculation, but is the concept clear to everybody? Yeah, tell me. Somebody was saying something. Please go ahead.
No, sir, just saying it's clear, sir.
It's clear. Okay. All right. One minor point here. This is R00R, right? So basically, this is a short form of writing the same thing, which is written here. So this part was my R matrix. We have discussed that, right? Cos, sine, minus sine, cos, and then 0, 0, 0, 0, 1 here. So this was my R matrix. RT matrix, this is not transpose. When I want to say transpose, I put this in the superscript. This is subscript T. Okay, that is for transforming a larger vector. So R was good for a 3-component vector. RT is good for a 6-component vector. Likewise, it could be, and there could be an RT for 12-component vector. So my RT looks like this basically after expanding R, 0. When I say 0, it is not a single 0. It is basically 9 zeros written like this. Okay, then 0 here, this 0 matrix, and then the R here. Fine, clear to everyone? We often write this cos gamma and sine gamma in short way by calling it CX and CY. Why CX and CY? Basically, what is happening is that, again, if you had a vector, let's say A, okay, and let's say A was unit vector, it had a unit length, then its projection on the x-axis will be cos gamma. Okay, if this angle is gamma, that is cos gamma, right? This length is cos gamma. But also I can call it this part a projection of unit vector, that is Cx and Cy. So its projection on x-axis will be Cx, its projection on y-axis will be Cy. So often cos gamma and sine gamma are also known as Cx and Cy. Okay, just to write it in a shorter way. Okay, so don't get confused when you see Cx. It's basically same as cos gamma. Okay, so far what have we learned? We have learned the following. We have learned transform a 3×1 vector from structural to member coordinate system, right? Right. And that one was basically, if it is a 3-component vector, M was equal to, just in case I don't make a mistake, was equal to R A S. These A's are vectors, or you can write them in a curly brackets. Okay, and this R is a matrix, and that R is given by Cx Cy minus Cy Cx 0 0 1 0 0. Okay, you have seen it several times, so I'm not spending too much time here. Okay, similarly, we can transform from M to S coordinate system by calling it AS is equal to R transpose AM. I'm just summarizing whatever we have learned so far. Again, a 3x1 vector or 3 component vector. Fine. Ideally, I should say 1x3 vector, but I'm just being lazy here. It's actually one row, right? A single row. So sorry. Is it a single row, right? So 1:3. Sorry. No, not single row. 3 rows, single column. Yeah, so 1:3. Likewise, we have learned if I have 1:6 vector, then we will do it. AM will be equal to RT AS, and my RT will be equal to nothing but R0 0 R, because this was a 6 component vector. Correct? This is for structural to member. Similarly, if I'm doing a member to structural for 1/6 vector, then I will be having AS is equal to RT transpose AM. Fine. This RT is still the same, but RT transpose will basically just make it we just have to take the transpose of this one. These are actually supposed to be inverse, but it turns out that for these transformation matrices, inverse is same as transpose, so we will simply use the transpose. That is easier to do. Okay, everybody knows what transpose is, right? What is the transpose of this matrix? 1 1 minus 1 1.
1 minus 1 1 1.
Okay, this is the transpose. So basically what we are doing is we are taking the line of symmetry, that is diagonal line, and then we are switching the members symmetrically upside down. Okay, so the lower triangle goes into the upper triangle comes into the lower triangle. Got it? Just to revise a little bit, I'm sure you are doing elasticity course, right? So you must have been very familiar with these concepts. Are you not? All of you have taken the elasticity course, right?
Yes, sir.
So a lot of matrix manipulation you must be doing in that course too. Okay, fine. So now coming back to our problem, we have learned how to transform a vector. We have learned how to transform a stiffness matrix. Okay, now I did not summarize that. And if we have a stiffness matrix, a 6x6 stiffness matrix, okay, and if I know in the member coordinate system, and I want to get the stiffness matrix in the structural coordinate system, what do I have to do? My S matrix in the structural coordinate system will be equal to RT transpose SM RT. Okay, that basically summarizes everything that I've learned in the transformation matrix, the transformation discussion so far. Please make a note of this, note down, keep it as a summary for your future purposes. Okay, likewise, if I had to get, and you hardly ever need that, so I'll not confuse you further. Okay. So this is basically what you need for your entire transformation calculations. And of course, you can expand it further. This is the way you transform a 1/6 vector. If you have 1/12 vector, I've already explained to you, your RT becomes larger. It has 4 times R. In this one right now, you have R coming only 2 times here and here. In that case, you would have R coming in 4 times. Okay. Fine. So coming back to our plane frame problem, in that problem we had two members. For the first member, we had developed the stiffness matrix in the local coordinate system. For the second member also, we had developed the stiffness matrix in the local coordinate system. And you can very easily see that there is no interference between axial behavior, that is 1, and flexural behavior, 2. So there is no zero terms between 1 and 2. Likewise, 1 and 8, 6 also there are zeros. That means axial and flexural behavior are not coupled. We had discussed this thing in the previous class. Right? So that's why you see all these zeros here. Axial and flexural behavior is not coupled. Fine. Now what happens is that we have to do the transformation for the global in the structural direction. So first one does not really require much transformation. Just to check whether our method was correct, what we will do is, this is the stiffness matrix of the first member in the local coordinate system. These are just by substituting the respective values. So in this example, if you can go back again one step. I cannot discuss that. So I have not given the values yet. Okay, so somehow the slides have become incorrectly arranged. These are some of the basic information. The E value is this much, KSI. L value that is given as here, this is L, this is L. So the length of the second member is how much? For the second member, length will be L square root of L square plus 9 by 16 L square. Correct?
5 by 4 L.
5 by 4 L. So for the second member, length is 5 by 4 L. For the first member, it is L. That is 100 inches. So the second one would have 125 inches, right? Yeah. IZ is given for both members, this many inches to the power 4. P values, these loads we have not discussed yet. Some forces are given, 1000 kip, 10 kips. So this W is also a function of P and L. So you can get the value of W. And area is given as 10 inches square. So if we take the cross-section properties and member properties from here, I substitute those, I'll get the stiffness matrix for the first member in number terms. Okay, so I have substituted the coefficients AX, E, etc. with exact numbers. And then this is the stiffness matrix in the local coordinate system. This is the stiffness matrix for the second member in the local coordinate system. Now comes the transformation. The first matrix does not really need any transformation because first matrix, the first member is already in the global transformation, or structural coordinate system. Okay, X and X are aligned, Y and Y are aligned, Z is of course aligned. So it does not require much transformation, but anyway, we will still try it. So this is the transformation matrix, Cx, Cy minus Cy, Cx, 0, 0, 1. This is R, R0, 0, R is the RT vector, RT matrix. Okay. So if I take the values of, if I take gamma as 0, then cos gamma, that is Cx, is 1. Sine gamma is 0, right? So you get 1, 0, 0, 1. And likewise, you will basically see that you get an identity matrix. All the diagonal terms are 1, the rest of the matrix is 0. So your stiffness matrix in the structural coordinate system will be RT transpose, which is again an identity matrix multiplied by the stiffness matrix multiplied by identity matrix, that is RT. Okay, so basically there is no change in the stiffness matrix. That is obvious. For the second member, however, we have to do the transformation. And if you see the second member, the global coordinates, the local coordinate system, that is local X direction, is from J to K, right? That's how we count it. So that's how we have prepared our stiffness matrix, where 1, 2, 6 are given, are mentioned first in the stiffness matrix, and 7, 8, 12 are mentioned later. So my X goes in this direction. That is local X. Now, if you see from the global X, that is XS, and this is XM. Okay, this is not exactly in the same sign convention that we had assumed during the transformation. During the transformation, we had said our XM is at an angle of gamma in the counterclockwise direction from XS. But here what we see is that XM is in the clockwise direction from XS, right? So this gamma is basically negative. This gamma angle, that is the rotation, is basically negative. So my cos gamma will be equal to 4 by 5, that is 0.8. How do I know that it is 4.5? Okay, so this part was L, this part was L, this is L, this is L, this is member 1, this is member 2, this is member 1, this is member 2. Okay, and this length, this height was 3 by 4L, right? Okay. So cos gamma will be, this is the angle gamma. So cos gamma will be equal to, so if this is 3 by 4, this is 4 by 4, that is 1. So the length is 5. So 5 divided by 4, or 4 divided by 5, that is cos gamma, 0.8. So likewise, sin gamma, this time will be negative, right? Because it is a negative angle. Minus 3 by 5, that is minus 0.6. We substitute the values into this RT matrix, 0.8 minus 0.6, 0.6, 0.8, and so on. You will get RT matrix. RT transpose SMS RT will give me the stiffness matrix in the global coordinate system. So stiffness matrix for the second member will be equal to RT transpose SM RT. How did I do this multiplication? These are basically two times I have to multiply. First, I have to multiply one of these and then this. Correct? So these two multiplications I did using. You can use Excel. Excel has an automatic multiplication, I suppose. Now it's easier. It's pretty easy to do multiplication, matrix multiplication, even in Excel. But otherwise, you can do in MATLAB. So I strongly recommend that you start using MATLAB for this kind of problems. Okay, so that will get you familiarized with matrix operations in MATLAB. Fine. So I did this matrix multiplication. These are 3 matrices to be multiplied. You can do it in a single command in MATLAB. Followed it. Everything is fine. Any doubts, questions? Concerns? No? Okay. So now this is the stiffness matrix in the global coordinate system for the second member. Right? So this is the second member. The global coordinate system basically means this is X, or this is the first degree of freedom system. If I can write this. So in the global coordinate system, I got 1, 2, 3, 4, 5, 6. This 6 is basically rotation in the Z direction. Okay. 4, 5, 6, 7, 8, 9. Fine. Now we are dealing with only, this is only for the second member. So that is basically what it means is that this stiffness matrix belongs to 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9. Okay. What you had earlier was the stiffness matrix that you had earlier was belonging to this, and then this rotation. Likewise, this, and then this rotation. Okay. So that was the original stiffness matrix. Now, in that stiffness matrix, this original one, you may remember that axial behavior and flexural behavior. That is this, if I may call it. I'm still calling it 4, 5, 6. Actually, the degrees of freedom were different, but I'm just calling it to keep a similarity between 4, 5, 6 here and here. You may remember that 4, the terms belonging to 4 had no non-zero relationship between the terms belonging to, with the terms belonging to 5 and 6 degrees of freedom, right? So that's why you had zeros here and zeros here. Remember that? But now you don't have those zeros here. Because when you introduce a unit deformation in 4th degree of freedom, in this degree of freedom, in this direction, it introduces axial behavior, axial response from the member. It also introduces a flexural response from the member. So 4 and 5, likewise, when you introduce 5, it is partly axial. That is basically if the member stretches or this joint moves by a unit here, it will be extending a little and it will also be flexing a little. Likewise for 4. So now what you are getting is 4 and 5 are coupled. They are not uncoupled anymore. Okay, it makes sense, right? Unlike what you had before. So earlier, for SM2, you may remember for the second member, these terms were all zeros. That means that behavior in the axial direction was uncoupled from the flexural direction. Now, flexural and axial, no, I should not say flexural and axial behavior is coupled, but the behavior in fourth and fifth are coupled now. Okay. Anyway, so these are the degrees of freedom. So 1, 2, this is first member, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Here it is 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9. These are, so this is for the first member, this is for the second member, stiffness matrices. Now we just need to assemble them. So we will assemble the degrees of freedom which are common between the two. So the first one has 4, 5, 6. The second one has 4, 5, 6 here. So this part is common. We will simply assemble the two. What will be the size of the global stiffness matrix now? The combined stiffness matrix. What will be the size?
9 by 9.
9 by 9, sir.
Exactly. So it will be 9 by 9. This 4 by 4, 5, 6, 4, 5, 6 will be common. So if you look at some of these terms, so the term 4, 4 here was 1000. The term 4, 4 here is 534, right? So after adding them together, I will get 1534, term 4, 4. Okay. So basically, I have simply added the terms. Wherever there were no values available from either matrix, we will put zeros here. Okay. Which again mean the same thing. When we have 0, that means there is no interference. So if I introduce a one displacement here in the 1 degree of freedom, it does not introduce any force in the 7th degree of freedom because in between it is restrained. Okay. Fine. Any questions so far? Now, what are the subsequent steps? We got the stiffness matrix in the global coordinate system for the entire structure. What are the next steps? What is the next step?
Separating the restrained and
Very good. Yes. So basically, after calculating the stiffness matrix, we can basically write it in that form here. A in the global coordinate system, I'm writing it AS is equal to S ds, right? In the structural coordinate system, displacements and forces in the structural coordinate system. Now, this same equation could be written as AF, A free and A restrained, AF AR, right? Was S down S FF, SFR, SRF, SRR, DS, or DF, DR. You remember that? The same thing we need to do now. But for that, I have to move the terms belonging to the free degrees of freedom on one side and the terms belonging to restrained degrees of freedom on one side. So which of the degrees of freedom, so there are total 9 degrees of freedom, 1, 2, 3, 4, 5, 6, 7, 8, 9 marked here. Which of these are free and which of these are restrained?
4, 5, 6 free.
Yes. So 4, 5, and 6 are free. So we need to move the degree, the terms corresponding to 4, 5, 6. So these terms, so basically these columns we have to move to the front. Likewise, these rows we have to move to the top so that SFF is sitting right here in the corner. That's what we do. We move the columns corresponding to 4, 5, 6 to this side. Then we move the rows corresponding to 4, 5, 6 to the top. So now we have broken this stiffness matrix into 4 components: SFF, SFF, SFR, SRF, SRR. Okay. SFF is free. This is free restraint. This is restraint free. This is restraint. Okay. So now I think we can start solving this problem again. How do we proceed now? Some of the details are added now. So the W value, W is given as 2.4 P by L. So this will be equal to, P is given as 10 kips. P is given as 10 kips, AX is given, E is given. We have already substituted A, E, and L values in the example before. I is also given, that also has been substituted in the stiffness matrix. The force values or load values are not incorporated yet. So P is 10 kips. So W will become how much? 2.4 times 10 divided by 100. So that is 24 divided by 100. That is 0.24. No, 24 divided by 100. Right? So 0.24. Okay. 4 kips per inch. Fine. Here it is. W is equal to 0.24. So now we will start solving this problem. We have developed the stiffness matrix in the global coordinate system. Now we should be able to solve this problem. So what do we need? We need the A matrix, whatever values we know. We don't know the values at the restrained degrees of freedom, but that is okay. And we need the stiffness matrix, right? Then we can solve for the D matrix. Fine. So A matrix is basically made of two components, A joints and A members. Correct? You remember? So what we were doing, A joints minus A FEM we were doing, right? For the forces that are acting on the member, we were taking a negative effect of those and we were calling them AFEM. And we were taking the total A, which was equal to A joint minus AFEM. That's what we were doing. We discussed that in the previous two classes. So first we will calculate A joints. So where are the joints? One joint is here, the second joint is here, the third joint is here, right? First one is here. So at these joints, at the first joint, there are no forces acting that we know of. There are reactions, of course, but not those forces. At the second joint, we have one P acting in the downward direction. So that is in the opposite of the global y-axis. So we will call it minus P. Okay, so that is in the fifth direction. In the fourth direction, there is zero force. In the fifth direction, we have minus 10. In the sixth degree of freedom, which is this one, we have a PL. So PL will be equal to 10 multiplied by 100. That is 1000. 1000 again in the clockwise direction. Okay, so these are not the internal forces. These are external forces. So clockwise and anti-clockwise will be the way to figure out whether it is positive or negative. That is minus 1000. So these are the joint forces. There are no other joint forces acting at any other location. Then there are member forces. There is one member force acting here, and there is one member force acting here. Right? So we need to find out how to calculate the FEM effect, fixed end moment effects, because of these. Okay. Now, for the first member, we will do it one step at a time. The joint force vector, we had done for the entire structure because they were all in the global coordinate system directly. For the member forces, we will do it in two parts. Fixed end moments for member 1, fixed end moments for member 2. Okay. So fixed end moments for member 1. Member 1 has this W acting, which is equal to 0.24. So what are the reactions for this? If this was a fixed member and there was a W acting on it, what are the vertical reactions? What is the vertical reaction at each end?
WL by 2.
WL by 2, right? And that is positive, correct? That is in the same direction as these arrows. Right? So WL by 2, WL by 2. So W is 0.24 multiplied by 100, that is 24 divided by 2, 12. So 12 and 12 in the second and fifth degrees of freedom. So this is 1, 2, 3, 4, 5, 6. So in the second degree of freedom and the fifth degree of freedom, I got WL by 2. What other reactions would there be? There will be moments and moments, right? How much is that?
WL square by 12.
WL square by 12. That turns out to be 200. Okay. So in the third degree of freedom, you got in the anti-clockwise direction, right? So I'm keeping it positive. But in the sixth degree of freedom, I got clockwise direction. That's why I'm calling it negative. Okay. So minus 200 on the sixth degree of freedom, that is this one. And plus 200 is this one. Agreed? So I got the end forces for member 1. The end forces for member 2, I have to calculate in the local coordinate system first. Okay, then we will do the transformation to get everything in the global coordinate system. That we will see in a minute. But the member is arranged like this, and the forces are acting this way. Okay, so I have to break this force. So this is, you can imagine that this is the member. If it is fixed. But the force that I'm applying is not aligned with the local coordinate system. It is aligned with the structural coordinate system. So first I have to break this force into local coordinate system. So the force here was 20, right? 2 times P. P was 10. So 20 kilonewton was acting here, which I can break into 2 components. The perpendicular component will be 12, and this component will be, this component will be 16, and this component will be 12. Okay. This is what I've done. That is 12. So there is a force acting in the axial direction that is equal to 12 kips, and there is a force acting in the lateral direction that is equal to 16. Agreed? Everybody agrees to this? 12 and 16 breakup of the 20 kilonewton force?
Yes, sir.
Okay. So now if I have 16 kilonewton acting in this direction, what are the end reactions? Force reactions will be 8 on each side. Okay. So that's what this 8 and 8 are. Both of them are positive because both of them are in upward direction. Fine. What will be the axial reactions? So 12 kilonewton is being applied in the axial direction. That has to be resisted by both sides. And since it is acting right in the middle of the length of the member, both sides will be offering same resistance. Okay. So how much will it be? 6 on each side. Okay. Half of 12. Okay. So since this is in the minus x direction, I'm calling it minus 6 and minus 6. Minus 6 and minus 6. Got it? What else needs to be handled? Will 12 contribute to any moment reactions at the ends?
No, sir.
No. Right? In the local coordinate system, your axial behavior is completely decoupled from the flexural behavior. Good. This 16 will, however, contribute. So what will be the moments? How much is the moment at a fixed beam for a point load?
PL by 8.
WL by 8.
PL by 8, yeah, WL by 8. So that is 16 multiplied by 100 divided by 8. Oh, sorry, not 100, 125. The length of this member is 125. Okay. So on the first joint, I have it in the counterclockwise direction. So that is positive 250. On the second joint, that is negative 250 because this is clockwise direction. Okay. So I got minus 250. So I got the member end forces for the second member in the local coordinate system. Now I had done this exercise before. Let me go back to this sheet. If I know any vector, so this was a 6 vector, right? 6 component vector. This is a 6 component vector. If I know the value of any 6 component vector in the member coordinate system, and I want to know its values in the structural coordinate system, this is a 6 component vector. What do I need to do? I need to take AS is equal to RT transpose AM. So I'll pre-multiply with RT transpose. Correct? So AM fixed end 2 in the structural coordinate system will be equal to RT transpose this one, whatever this is. Agreed? Okay, because in this current position, I cannot simply, in this present situation, this is in the local coordinate system, this. The vector that is given here is in this coordinate system, which is different from this coordinate system. So I cannot add the terms corresponding to this vector and this vector. First I have to transform this vector in the global coordinate system. So this is the vector in the local coordinate system. This we just calculated 0, 12, 200. 0, 12, 200 for the first member. So no transformation required. For the second one, however, in the global coordinate system, it will be RT transpose multiplied by AM2 local. So AM2 local was 0, 10, 250, if you remember. I'm sorry. Let me go back. No, I mean, this one was 0, 12 to 0, okay, 0, 8, 250. Huh? So this one, AM was 0, 8, 250, and so on. Correct? But when you do this pre-multiplication with RT transpose, what you get is 0, 10, 250, basically, and so on. So you can see that the moment values have not changed. Moment values were 250 here. After transformation, it remains 250. Basically, I have pre-multiplied with this vector, this matrix, and this is what I got. But the forces have changed. So initially, it was -6 and 8. So -6 has become 0, and 8 has become 10. You can physically also see you had this vector, you had this force acting, or sorry, this member and this force acting, and this was the global coordinate system. If I had asked you 20 kilonewton force is acting, what would be the reactions? So moments we had calculated correctly. Moments need not be changed, 250, 250. What would be the reaction? You would simply say the vertical reactions will be 10 kilonewton on each side, correct? And there would not be any horizontal reactions. These will be zeros. That's what we got after transformation. Okay, and vertical reactions are both 10 kilonewton, 10 kips. Make sense? So we could have directly solved, we could have directly calculated the fixed end moments in the global coordinate system. Still, we would have got the same answer, 0, 10, 250, 0, 10, 250. But somehow, even after transformation, you got the same answer. Make sense? Were you able to follow what we did?
Yes, sir.
For the first member, there was no transformation required. We got the end, the fixed end moments and reactions for the first member, which were calculated in the local coordinate system. Same we can use in the global coordinate system. For the second member, we had this vector, which we calculated before. This one. This we pre-multiplied with this RT transpose that is given here. And we got AMFE2. This is that vector. That's all. Okay. And we could have done this directly also, but it's better to do it in a methodical way so that you can develop a program. Okay. All right. So we had developed our S matrix. From the S matrix, I can take SFF matrix that was 3 by 3 matrix in the submatrix of 3 by 3. This is the SFF matrix. I can take it apart, take it separately. That is that SFF matrix 3 by 3. Then I've got my A vector. Okay, so I had got a joint vector and a element vector, which is basically a FEM vector. And that is a combination of for member 1 and member 2 in the global coordinate system. So I got the a FEM values for the first member, 0, 12, 200, and so on. That is this one. Okay. And then for the second member, 0, 10, 250, and so on. That is this one. Okay. I can add the two for the first and the second member, and I get this one. Here, if you notice, the components corresponding to 4, 5, and 6 are still in the middle. They need to be brought to the top. So what we do is we do two operations together here. The total A total was equal to A joint minus A FEM, right? So that's what I've done. A joint minus A element or A FEM. So this was A joint minus this was A joint. This is A FEM. Sorry. This is A FEM. A joint minus A FEM will give me some vector. Then what I do, I take the components corresponding to 4, 5, and 6 and move them to the top. So the component corresponding to 4, for example, this was 0 here. This was 0 here. So 0 minus 0 is 0. That remains here. This fifth component was minus 10. This was my 22. Minus 10, minus 22, minus 32. Minus 1000, minus 50, minus 1050. Likewise, component 1, 2, 3, and 7, 8, 9 are at the bottom. Okay. So out of this vector, the first three components belong to AFC. The last three components belong to ARC. C stands for combined. Okay. So F is free combined. R is distinct combined. Combined means joint plus element. Got it? So now what have I got? I have got my AF. I've got SFF. What can I use this for? I can write the equation as AF or AF minus AF FEM, whatever you want to call it. So that's why I'm calling it AFC is equal to SFF DF, right? So AF was this one that we just calculated. That is corresponding to degrees freedom 4, 5, and 6. But is equal to SFF DF. And no, why no terms of SFR DR?
Because DR is 0.
Yes. Ideally, this term should be there, but there is no DR, non-zero DR. All the DRs are 0. All the fixed degrees of freedom have 0 movement, so that part is 0. So I got this equation to solve. And again, this is a 3 by 3 matrix to invert. Okay. So I can invert this 3 by 3 matrix, or you can, I mean, basically, probably I have done it using MATLAB. So you can solve for D4, D5, D6 by using these 3 equations. And these are the values I got in inches. So these many inches, and this is radians. Okay, 6 is radians, and these 2 are inches displacement. Okay, so I got the displacements in the 4th, 5th, and 6th degrees of freedom. Of course, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So, of course, 1, 2, 3, and 7, 8, 9 are restrained. Only 4, 5, 6 were free, and these are the displacements there. Any questions so far? Now we have solved the system. Basically, we have calculated some displacements. Once we know the displacements, we can back calculate and get the values of all the internal forces, etc. That also we will discuss briefly. No questions, right? Okay. So now we have calculated the displacements. Now you will see the utilization of, or the utility of, these other components of this equation. This equation is a very powerful equation. So far we have been using only the first part of this. AF minus AF FEM was equal to SFF DF. Okay, and SFR DR also, but DR was always 0. So this part we have been using. Now we will see how to use the second part, which will help us solve for the reaction forces. So the AR are the forces at the locations where there is movement is restrained, which is nothing but your reaction forces. So AR minus AR FEM. Okay, so we can get AR FEM values also. AR minus AR FEM is equal to SRF DF plus SRR DR. Again, SRR DR will be 0 because DR is 0. So that part will go away. But what you are left with is AR minus AR FEM. If it was in the left hand side, AR minus AR FEM is equal to SRF DF. Correct? Or in other words, AR is equal to AR FEM plus SRF DF. Fine. Now, we had developed the entire S matrix. Remember? So it had terms of SFF, SFR, SRF, SRR. And we need to use this term of SRF. That is this term. That will have 3 by 6 matrix. Okay. So what do? AR we need to calculate. Basically, we want to know how much reactions we have at these 6 joints, at these 6 degrees of freedom. I'm sorry, at these 2 joints. What are the reaction values? So that is AR. This will be a 6 component vector, right? That is AR. AR FEM will be on the, I've taken it to the right hand side, AR FEM, which are basically corresponding to these degrees of freedom in the global coordinate system from the fixed end moments. So let's look at these degrees of freedom. So you remember I call it 1, 2, 3, then 4, 5, 6 are not there, then 7, 8, 9. So in the FEM vector, we have to look for the components 1, 2, 3, 7, 8, 9. Let's go back. These are those components 1, 2, 3, 7, 8, 9, right? That is Sorry, my mistake. Only FEM, right? The A element. Yeah. So here we will look at, this is 4, 5, 6. So that's what we're going to look at. 1, 2, 3, then 7, 8, 9. So 0, 12, 200, 0, 10, minus 250. Remember these values. 0, 12, 200, 0, 10, minus 250. That's what we should have. 0, 12, 200, 0, 10, minus 250. Okay. So that is your fixed end moments for the corresponding degrees of freedom. 1, 2, 3, 7, 8, 9. Plus SRF plus SRF multiplied by DF. Okay. And DF we have just calculated, minus 0.0202, minus 0.090, 0.099, minus 0.001. So all those values here. Okay. So this is all coming from the same equation here. And we can very simply solve this. We just have to multiply these two matrices and add with this vector. We will get these values. So these are the reaction forces AR at these 6 degrees of freedom. 1, 2, 3, 7, 8, 9. Fine. So we have solved for all the displacements and all the reactions. Pretty much we have solved the problem now. Correct? These reactions are in which coordinate system? Are these in the member local coordinate system, or they are in the global coordinate system?
Global coordinates.
Global coordinate.
How do we know that? How do you know that this is global coordinate system? Because this equation was written in the global coordinate system. This AR, this is all in the global coordinate system. This S matrix that we are talking about is in the global coordinate system. These deformations are in global coordinate system. Okay. We can write similar equations in local coordinate system also, but this is written in the global coordinate system. So this A's that we are getting, these are on global coordinate system. Okay. These are marked here, 1, 2, 3, 4, 5, 6, 7, 8, 9. Fine. So I got the reaction forces in these 6 components. Now, what else are you required to do when you say I have to solve a problem? So you have to calculate internal forces, right? Also, you have to calculate displacements, you have to calculate reaction forces at the boundaries, and also you have to calculate internal forces. Okay. So internal forces also can be done quite easily. For that one, we will write an additional equation. So these equations, you can see, these equations are valid for the global coordinate system. But we can also similarly write an equation for the local coordinate system. Let's say these are the forces acting. If I have a member, there are certain forces acting along the length of the member, and because of that there is FE moment, FE force. Okay, and there are some forces acting at the joints also. So A joint, that is basically your internal forces, minus AFE, or A element you can call it. Okay, fine. In the local coordinate system, I'm writing all of this, will be equal to SM in the local coordinate system multiplied by D in the local coordinate system. So all of these things have to be in the local coordinate system. That is also perfectly valid. Or the member coordinate system. Fine. Now the issue here is that SM in the member coordinate system, I know that for each member, right? Because before I developed the global stiffness matrix, I had the stiffness matrices for individual members in the member coordinate system only. I had transformed them to get the stiffness matrices in the structural coordinate system. So I had calculated the stiffness matrices in the local coordinate system or member coordinate system once. So I have those values still stored somewhere. I'll fetch those. Displacements in the global coordinate systems were calculated, but they were not calculated in the member coordinate system ever. So that we have to do. And then AFE were also calculated in the member coordinate system in the beginning. So that also is known to us. Then we can calculate the internal forces in the member coordinate system from that. Only thing that is missing here is displacements in the member coordinate system. Okay. But what we know already, which displacements do we know? We know displacements in the global coordinate system. So we know the displacements in global coordinate system, and these, for any given member at a time, you have 6 degrees of freedom in a plane frame, 3 here and 3 here, correct? So 6 degrees of freedom. And I know some values in the structural or global coordinate system. I know the value in structural coordinate system, I want to know the value in member coordinate system for a vector that is 1:6 in size. All I have to do is pre-multiply with RT. Okay. So if I pre-multiply with RT of that member, then I will be able to get the displacements in the local coordinate system. This is the displacement in the local coordinate system. Okay. Then this equation can be used. This is for each member using the stiffness of the member itself. So for the first member, SM1 was given as this one. You can go back and check. This was the stiffness matrix of the member in the local coordinate system. The RT is basically identity for the first member because it is in the same coordinate system as the global coordinate system. AMFE we had calculated this one, and from there, DJI we have just calculated. There are 1, 2, 3, then 4, 5, and 6. This is 4. This is 5. Okay, so we got some displacements at 4, 5, and 6. Those are those values. So this member 1 would have degrees of freedom 1, 2, 3, 4, 5, 6, and the values corresponding to displacement values corresponding to 4, 5, 6 are given here. This is in the global coordinate system, but same would be true for the local coordinate system because your RT is identity. Okay, so I substituted these terms DJI, RTI, SMI, and AM local. I substituted them and I will get the end reactions or internal forces at the ends for this member. That is what it is. Fine. Similarly, for the second member. For the second member, this was the stiffness matrix we had developed in the local coordinate system that will go into RTI. This was the displacements we calculated. So for the second member, we had 4, 5, and 6, 7, 8, and 9. Out of these, 4, 5, 6 values are given here. Okay. So this is in the global coordinate system, but we want to calculate that in the local coordinate system. So that's why we are pre-multiplying with RTI. So this RTI goes in there, and this DJ goes in there. We pre-multiply this with this, and we will get the displacements in the local coordinate system, which will be this, this, and the rotation. Okay, that we will do. AMFE local we had calculated in the very beginning, that we can put here, and by substituting that, I can also get AM2 local. So for the first member, I got the local reactions, which are turning out to be this. That is, these are basically internal forces combined with reactions, but in the local coordinate system. And for the second member, I got these end reactions, which are also internal forces for the structural point of view. And you got moments in the local coordinate system, the reactions. So this is basically your shear force. This is how the shear force can be calculated. These are basically axial forces, right? So you could not use the information about external forces directly to calculate axial forces. For example, see here, if you remember in this slide, we had calculated the reactions, ARs. These were 20, 13, 436. So 20 basically meant that there is a force acting 20 here, there is a force acting 13 here, and there is a moment acting 436 here. Likewise, there is a force acting minus 20 here, there is a force acting 40 here, and there is a moment acting 889. Okay, so moment might still be okay, but this force 20 does not necessarily mean, was not really equal to axial force in this member. What we actually want to know is what is the axial force and what is the shear force. But this 40 and 20 don't tell me what is the axial force and what is the shear force. However, when we solve it for the internal forces, we get that the axial force is actually 40.73 and the shear force is 20.53. Okay, that we can use directly, and that is at this end, and then intermediate calculations we can do based on this end forces and the internal forces that were applied. Okay, so this is how you solve a full plane frame problem. In the next slides, in this process, we had used this stiffness matrix, ASM. This we had discussed already. This was the stiffness matrix for the plane frame member. This was the RT matrix for the stiffness and the vector transformation. Here, the next two slides, slide number 60 and 61, basically summarize the entire process. So you don't have to memorize it. These are very critical slides which summarize the entire process and all the concepts required to solve all the subsequent type of structures. So we have solved a plane frame, but there may be space truss, plane truss, space frame, grid, whatever type of structure you have, whatever the information given in slide number 60 and 61 does not change. The entire process is already given here. You just have to follow this process step by step. The only thing that will change here are these two things. This RT, right now it is R00R. It may change its size. The R itself will change its size, or this matrix will change its size. So it will become R000 and so on. Okay. And the definition of SMI. So SMI right now was a 6 by 6 matrix for a plane frame. It may become a 3 by 3 matrix for some other problem. It may become 4 by 4 matrix for some other problem. It may become 12 by 12 matrix for some other problem. Okay. So only this RT changes and SM changes, and then of course RT transpose changes. But other than that, the rest of the procedure is exactly the same. I have just completed this entire process. I don't want to go through it again. It will be boring for you also. But please go through this slide. These two slides are very critical, 60 and 61, to understand the entire process. Okay. Can we stop here today? We will start with plane truss and space truss problems in the next class. If you have any questions, doubts, we can discuss those.